Hey guys, what's up? Welcome back. I totally screwed this up earlier. I was trying to live stream this lecture and totally screwed it up. So I'm doing a video, record a video, just gonna do the whole lecture and get this right this time, hopefully, and get it out to you guys. But today is section 13.3, Arc Length and Curvature. I should be able to get through it all now since I'm just recording it, so I'll just post it all in one video. But yeah, today, 13.3, Arc length and curvature. The first thing we want to talk about is arc length, and we get into curvature later. But arc length is just the length of a curve if you were to like completely stretch it out. It's kind of like the perimeter of a circle or a perimeter of some object. You know, it's like taking a string and wrapping it around that object. Well, arc length is just like the length of the curve, or the length of that perimeter. So curve C setup really is to just say a curve, suppose curve C is given by R of t equals f of t I hat plus g of t j hat plus h of t k hat. So that's our setup, and t is going to range between two values a and b, so those two values, and then we just have some curve in space, you know, something that looks like this. Could be three-dimensional, could be two-dimensional, it doesn't really matter. And we have some starting point r of a, we have some ending point r of b. And we want to find the total length of this curve if we were basically just to stretch it out and measure it with a ruler or some measuring device or whatever. So we want to know how long is this curve. So what we're going to do is we're going to take the domain t and break it up into a bunch of little pieces here. So this is the domain t, time, and let's say this is a over here and this is b over here. And if we cut it into small little sections, so call this like spacing here delta t, and we call this maybe ti minus 1 and call this point ti. Well, if we look at the curve corresponding to those 2 points, we get r of ti minus 1 and r of ti. And we get a differential amount of arc length, call it delta s, between those 2 points. So we get a little bitty bit of arc length between those 2 points. And we'll call those points xi minus 1, yi minus 1, and zi minus 1. And then this point we'll call it xi, yi, zi. So we want to find the little bit of arc length between those 2 points, so we can use the distance formula because it's approximately a straight line. So delta s is approximately the straight line distance, which is just the square root of, we'll call it xi minus 1 quantity squared plus yi minus minus 1 quantity squared plus zi minus 1 quantity squared. So that will be what we'll call delta zi, or delta xi squared plus delta yi squared plus delta zi squared. So just taking the little changes in x, y, and z and squaring them. And that's approximately delta s. So the little differential amount of arc length right there. We'll call it delta si because it's like the arc length over that little section. And now, if we want to find the arc length of the total, or the whole curve, we just make a bunch of little straight lines and approximate the curve with those straight lines, add up those distances, and that would be approximately the arc length. So s, the total arc length, will be approximately the summation I equals 1 to n delta si. Okay, which would be the summation I equals 1 to n square root of delta xi squared plus delta yi squared plus delta zi squared. So that would be approximately the arc length s. So then the total arc length, you probably see where we're going. The total arc length s is s equals the limit n goes to infinity summation I equals 1 to n square root of delta xi squared plus delta yi squared plus delta zi squared. So we take the limit of the Riemann sum to get the value of the integral. So this is going to be, or the total length of the curve. So this is going to be an integral of square root, and now we call it dx squared plus dy squared plus dz squared. And we can say that's just the integral over the curve C ds, differential arc length. So that's what we define as the differential, or the integral with respect to arc length, the total arc length, adding up all the little differential amounts of arc length. So really, this is not a super practical way, although it's the definition, it's not a practical way to calculate arc length. So not practical without a computer. With a computer, of course, this is exactly what you do. You use a Riemann sum to calculate the value of an integral. But for our purposes, doing stuff by hand in calculus and theory, the best thing to do at this point is to modify this a little bit using differentials. So for our purposes, we're going to say s is going to be integral from c, or over the curve c, square root of, and I'm going to do something that may be like a little bit frowned upon by mathematicians or whatever, but I'm just going to say dt over dt squared times dx squared plus dy squared plus dz squared. So dt is a derivative of t with respect to t, which is 1. So its squared is still 1. So I'll multiply that inside the radical there. And now I'm going to do, this is the forbidden part, I'm going to break those differentials up like a fraction and rewrite this as square root of dx dt squared plus dy dt squared plus dz dt squared, dt outside. So I'm basically pulling a dt squared out of the radical as dt. So this is a much more practical formula for integration. So what I'm going to do is say this is the integral from a to b as far as t is concerned. And up here we can see that dx dt is f prime of t, and dy dt is g prime of t, and dz dt is h prime of t. So that is our, those are going to be our derivatives. So that's basically f prime squared plus g prime squared plus h prime squared, take the square root. Another way we could write that is, well, that's like r prime magnitude. So this is the magnitude of r prime of t dt. So that is the practical formula for calculating arc length by hand. So this is practical for hand computation. And it's exact. It's the exact answer. Okay, so if we highlight this as its own formula, then the arc length S is equal to the integral from a to b magnitude r prime of t dt. So that is the formula we're going to use when we're calculating arc length. So let's look at an example of finding arc length. So example, the example says find the length of the curve. Find the length of the curve C given by r of t equals t squared comma 2t comma natural log t, and t goes from 1 to e. So that's our curve. I don't care what it looks like, to be honest. I can use the formula and calculate the length of the curve regardless. And that's the beauty of calculus usually, is like sometimes you get insight from doing the calculus versus like graphing it initially. You can kind of get insight from the calculus before you graph it. So what we're going to do is, to use this formula, we need r prime of t. So we take r prime of t, and that's going to give us a vector function 2t comma 2 comma 1 over t. So differentiating each component of the vector function. And then we need to take the magnitude of that. So magnitude of r prime of t is going to be square root of 4t squared plus 4 plus 1 over t squared, which means our integral s is going to be the integral from 1 to e of the square root of 4t squared plus 4 plus 1 over t squared dt. So you have to integrate that function to get the length of the curve. So don't freak out. This is actually very standard for these arc length problems. So there's a strategy for doing these arc length problems. The hints are, first thing to try is try to find a perfect square under the radical. So that's the first thing you want to do, is try to find a perfect square under the radical. Second thing, if you can't find a perfect square, is try a u sub. Maybe it's a nice linear function under the radical, you could do a u sub. If that doesn't work, maybe you could try a trig sub. Try a trig sub to evaluate the integral. Maybe it's a square under the radical, but then there's no function outside, obviously, to do the integral with the u sub. So maybe you can try a trig sub if it's like t squared plus 4 or something under the radical. Then you could do a trig sub. So we're going to try to find the perfect square part, and we're going to note that 2t plus 1 over t quantity squared is equal to 4t squared plus 4 times t over t plus 1 over t squared, which is exactly equal to 4t squared plus 4 plus 1 over t squared. So in this case, there is a nice perfect square under that radical. So this is integral from 1 to e square root of 4t squared plus, whoops, we're factoring it, 2t plus 1 over t quantity squared dt. And take the square root of a square, you get integral from 1 to e, absolute value 2t plus 1 over t dt. So all of that in absolute values. And the second thing we want to note is that 2t plus 1 over t is greater or equal to 0 on the interval 1 to e. So those functions are both positive, so their sum is going to be positive. I don't have to do anything crazy with this integral for absolute value. So that's just going to be integral from 1 to e 2t plus 1 over t dt. And that evaluates to a nice easy integral of t squared plus natural log absolute value of t from 1 to e. and we plug in those bounds, we get e squared plus natural log of e minus 1 squared minus natural log of 1. And natural log of e is 1. 1 squared is 1, so those cancel. Natural log of 1 is 0, so this is eventually just going to become e squared plus 1 minus 0, which is just e squared. So a nice answer to our problem. Okay, so the next thing we want to discuss is the fact that, just make a note in your brain, arc length should not depend on the parameterization used. Parameterization used. Right, it shouldn't, the curve doesn't care how we describe it. Parameterization. The curve just cares about how long it is. It's just some object. You know, the string doesn't care, you know, how I choose to describe it with math. It's just the string and I want to know the length of it. So, for example, what do I mean? I'll give you two parameterizations for the same curve and show you that they both give the same arc length. So, the helix is given by, or I should say a helix is given by r1 of t equals cosine t comma sine t comma t, where t ranges from 0 to 2 pi, and r2 of t equals cosine of 2t comma sine of 2t comma 2t, where now t could range from 0 to pi. So it's the same helix circling around the z-axis, but just different parameterizations. So if I kind of draw this helix to give you an idea of what it looks like, it's kind of going around. X and Y are like in a circle of radius 1, and it's going from z equals 0 down here to z equals 2 pi up here. It's just different parameterizations, but they're describing the same helix. Okay? It doesn't matter how you describe the helix. The curve has its length, and it should be the same regardless. So we're going to show that the curve, the arc length of the curve is the same regardless of which parameterization is used. So solution, find the arc length using both R1 and R2. So we'll call it S1. It's going to be the integral from 0 to 2 pi, magnitude R1 prime of t dt. So I need R1 prime. R1 prime is going to be negative sine t cosine t1. And R2 prime is going to be negative 2 sine 2t, 2 cosine 2t, and 2. So that is our, or those are our derivatives. So now let's take the magnitude of the first one, integral from 0 to 2 pi, square root of negative sine quantity squared is sine squared t plus cosine squared t plus 1 squared dt, which is integral 0 to 2 pi What do I know from trig? Trig is, or trig tells me this is just 1. So that is going to be square root of 1 plus 1 dt, which is square root of 2 times t from 0 to 2 pi, which is 2 pi times square root of 2. So that's the length of this helix. If I were to stretch it out in one long straight line, it would be this long in inches, meters, feet, whatever it is. So now if I use the second parameterization, I should get the same things. S2 be the integral from 0 to pi, magnitude r2 prime of t dt, which is the integral from 0 to pi, square root of, and now take the magnitude of r2 prime. So that's going to be 4 sine squared 2t plus 4 cosine squared 2t plus 4 dt. So I square each component and add them all together. Again, trig is going to tell me these two add to just give me a 4, because I can factor out a 4 and I get sine squared 2t plus cosine squared 2t, that's just 1. So this is equal to square root of 8 integral 0 to pi dt, which is going to be 2 square root of 2 times t from 0 to pi, which is 2 square root of 2 times pi. That's the exact same answer. So arc length does not depend on the parameterization used for the curve C. So from there, the next thing I want to do is talk about the arc length function. So definition, the arc length function s of t is given by s of t equals the integral from 0 to t, magnitude r prime of integration variable, I'll use u du. So it doesn't really matter what you use for the integration variable. I don't want to use t because that's my variable upper bound. Sorry, why did I put 0? It should be from a to t. So arc length function is given by this function here, integral from a to t. So basically it's saying, okay, how much arc length do I have? Well, you really depend on the parameter, like how far along the curve have you gone? Well, that's given by the t value, or the time. Once you know that, then you can figure out the arc length by integrating up to that time. So if you plug in t equals b, you get the total arc length. So this is the arc length function, and then from there we want to note by fundamental theorem of calculus part 1, we have ds dt is equal to magnitude r prime of t. So that's an extremely important formula we're going to use in this class and in vector calculus next quarter. So that's an extremely useful formula, ds dt equals magnitude r prime of t. But another thing to note is that the differentials work out so that, of course, ds would be magnitude r prime of t dt. So that's the differential equation. ds equals magnitude r prime of t dt. And that's also an extremely useful equation. We'll make use of it in vector calculus numerous times. So just keep these two stored in the back of your brain somewhere. They're going to be extremely useful in the future. They're kind of core to the idea of arc length in the first place, so they're very, very important. Okay, so what can we do now? What can we do? We can say that actually this arc length S because it depends on where you are on the curve, it could actually be a parameter for us. So we can actually make S the parameter for R, which is our vector function. So our vector function can actually be a function of arc length, and then I'll know exactly where I am on the curve if you tell me how much arc length I've got from my starting point. So you have some curve, and you know this is your start point and this is your end point, and I tell you S equals, I don't know, 2. S equals 2 tells me I'm right here on the curve. So I can actually parameterize my curve as a function of the arc length, and we call that reparameterization of a curve with respect to arc length. So this is called reparameterizing a curve with respect to arc length. Because essentially we start out with a function of t. Well, if we can get the arc length function s of t, we could hopefully invert that to get t of s and plug that back into our function r of t to get r of s. So example, let's reparameterize the curve with respect to arc length. So reparameterize r of t equals 3 sine t, comma 4 t, comma 3 cosine t. T goes from 0 to 2 pi. So reparameterize this curve with respect to arc length. So basically make this a function of arc length. So make the parameter for r be arc length. So what we need to do is find s of t, invert it, and then sub into r of t to get r of s, which is just r of t of s. So what we're going to do is we're going to find s of t. So that's the first step. Second step, third step. So s of t is going to be the integral from 0 to t, magnitude r prime of u du. So I'm going to rewrite it as r prime of u. R prime of u will be equal to 3 cosine of u, 4, and negative 3 sine u. So that'll be the integral from 0 to t, square root of, well, square those, add them together. So 9 cosine squared u plus 16 plus 9 sine squared u du. Which will be integral from 0 to t of square root 9 plus 16 du, which is square root of 25, which is integral 0 to t 5 du, which is just 5 times t. So the arc length function s of t is just 5 times t. So far we've got s of t equals 5 times t, which is an increasing function. Nice one-to-one function. T is going from 0 to 2 pi. So from there we would know that s would range from 0, s of 0 equals 0. It's the that's the minimum arc length, and then s of 5 would equal 10 pi, and that's the maximum arc length. That's the total arc length. So s ranges from 0 to 10 pi. And from here, we can invert this and say s equals 5t implies that t equals s over 5. And now sub this into r of t to get r of s. So that would be r of s equals, we had 3 cosine of t, sorry, we had 3 sine of t, but now t is s over 5, comma, 4t, well that's 4 times s over 5, and then 3 cosine s over 5. And s ranges from 0 to 10 pi. And that is our vector function parameterized in terms of arc length. And then from there, we just want to note that since s is independent of parameterization, this is the only way to parameterize the curve in terms of s, which is the arc length. So parameterization with respect to arc length is unique. All right, so for curvature, what we're going to do is we're going to start off by just trying to think about the concept of what curvature is. So if we think about curvature, we would say probably on the left, there's less curvature than there is at the right, or on the right. So actually curvature is more of a local thing in that each point has its own curvature. And curvature, we would say probably the curvature here is greater than the curvature down here. Whereas over on the right side, we'd say the curvature at the bottom here is probably less than the curvature up here at the top. And then definitely less, or there's less curvature on the right definitely than there is on the left, or whatever. So the curvature is really just how quickly is the tangent vector changing as you get closer and closer to that point. So the tangent vector seems to change a little bit, but then it seems to not change at all on the left. Whereas on the right, it seems to change and it changes, but then it starts to change a lot around this point. And then it kind of flattens out over here on the right, like the tangent vector almost seems to stop changing. So the curvature is a very local, concept, and it's really just the rate of change of the tangent vector as you move along the curve. So definition, the curvature of a curve C is given by, we call it kappa for curvature. Kappa equals the magnitude of the rate of change of the unit tangent vector divided by, or with respect to, arc length. So the unit tangent vector, capital T, how does it change with respect to arc length? So S here is the arc length parameter. So basically we are differentiating with respect to arc length. So how quickly does the tangent vector change with respect to arc length? Okay, well, this is great, but it's not very practical. This is, yeah, this formula here is not practical at all. So what we're going to do is use some calculus to modify it a little bit and get it into something we can actually compute if we have like a parameterization and things like that. So by the chain rule, we could say that dt ds could be written as derivative of tangent vector with respect to some parameter t times derivative of some parameter t with respect to arc length. And then we can use like a little calculus and algebra kind of mixed together. Again, it's not very great to say it like that, but we can just say derivative of tangent vector with respect to parameter t divided by ds dt. And then we can say that that's actually, we could just call that capital T prime of little t over magnitude r prime of t, which we just talked about with arc length. So ds dt we know is just magnitude r prime of t. So that's a nicer formula for that derivative dt ds. So curvature, we can actually say kappa of t can be written as magnitude of capital T prime of little t over magnitude r prime of t. And since the bottom is already non-negative, we can just put the magnitude on the top. So it's magnitude capital T prime little t over magnitude of r prime t. And that is a very practical formula for calculating the curvature. So that's a first, we'll call it a first formula for calculating curvature. We'll have another formula because this formula sometimes breaks down, so we'll get another formula in a little bit, but we'll use this one in our first couple of examples, at least as far as we can, to calculate the curvature. So example number 1, the first example says show the curvature of a circle is constant. So constant curvature for a circle, which means every point on the circle has the same curvature. So what we're going to do is just start off with any circle. So we're going to let x squared plus y squared equal r squared be any circle. So capital R is the radius of just some arbitrary circle. And what we're going to do is parameterize that circle. So parameterize that circle. And what we're going to do is say x equals capital R cosine of t, y equals capital R sine of t, and t ranges from 0 to 2 pi. So then our vector function, r of t, is equal to r cosine t, r sine t, and then r prime of t is equal to negative r sine capital R cosine and the magnitude r prime of t is equal to square root of capital R squared sine squared plus capital R squared cosine squared, which is square root of r squared, which is r. Because r is positive, I don't need absolute values. So that's the magnitude of this r prime of t. So that's going to be our denominator when we're doing the curvature. Just remind ourselves of what the curvature formula is. Kappa of t is going to be magnitude capital T prime over magnitude r prime. So we already have the denominator there. What is capital T though? Capital T, unit tangent vector, is r prime over magnitude r prime. So that's going to be 1 over r times r prime, which is negative r sine t comma cosine t. Whoops, capital R cosine t. So dividing by r, we just get negative sine t comma cosine t for capital T of t. So that is our unit tangent vector. Now we actually need to take the derivative of this vector. So capital T prime of t is going to be negative cosine of t comma sine negative sine of t. And then we need to take its magnitude. So magnitude of capital T prime is going to be square root of cosine squared t plus sine squared t, which is 1. So curvature for a circle at any time t, or any value of parameter, is going to be 1 over r. So that is the curvature of a circle. So curvature of a circle, not too bad. It's constant, that's nice. What about the curvature of an ellipse? So example, find the curvature of the ellipse parameterized by r of t equals 2 cosine t comma 3 sine t. T ranges from 0 to 2 pi. Okay, we'll just try the same thing. So solution, I need r prime of t, which is going to be negative 2 sine t, 3 cosine t. Magnitude r prime is going to be square root 4 sine squared plus 9 cosine squared. This is getting to be a little bit trickier because it's not going to be a constant here for magnitude r prime. So this is going to be square root of, could break it up as 4 sine squared t plus 4 cosine squared t plus 5 cosine squared t, right? Because 4 plus 5 is 9. So I could break it up this way, and then the first two, 4 sine squared plus 4 cosine squared, that's just 4. So I could say square root of 4 plus 5 cosine squared t. So that's magnitude r prime. Eek. So capital T is going to be r prime of t over magnitude r prime of t. So that's going to be 1 over the square root of 4 plus 5 cosine squared t times negative 2 sine t comma 3 cosine t. Yeah, this is getting nasty. So negative 2 sine t over square root of 4 plus 5 cosine squared t comma 3 cosine t over square root of 4 plus 5 cosine squared t. Frowny face, this is not looking good. So now differentiate. Really? Then take the magnitude? That's I'm gonna go with that's a big nah fam from me. So actually there's another formula for curvature, and I have a link to a video that derives this formula, and you can watch it if you want. I find some people like it, some people find it interesting, some people feel like they need it for the background, but honestly most people just memorize it. Like if you have to rederive the formula the whole time, like it's going to be way too much time. So it's either you just remember the two formulas or you have to rederive everything every time. So in my opinion, it's easier just to remember the formula. So the second curvature formula, so try another formula for curvature. Kappa of t, and I'll link to the video that derives this. Kappa of t can be written as magnitude r prime cross r double prime over magnitude r prime cubed. So that is another formula for curvature that works regardless. So if the first curvature formula doesn't work out so well, you just use this one, and this one will most likely be good to go. So let's do that for this ellipse problem. So let's try the ellipse, but do the second curvature formula. So this we'll call it the second curvature formula. I actually haven't looked to see if there's like a third curvature formula. Actually, I guess you could say there is with like tensor calculus, but I'm not going to go there for sure. So let's use this to calculate the curvature. So we already got r prime. Let me just copy some stuff down. R of t we know is 2 cosine comma 3 sine. R prime is -2 sine comma 3 cosine. And now we need r double prime, which is going to be -2 cosine comma -3 sine. We're going to need magnitude of r prime. Yeah, magnitude of r prime, which you already found to be square root of 4 plus 5 cosine squared t. And then let's take the cross product. We need the numerator, which is r prime cross r double prime. I've already kind of got it set up in a nice IJK format, so I put an IJK, and basically k is 0 for this 2D vector. So the vector is already going to only have a z component. So the z component is going to be 6 sine squared plus 6 cosine squared, which is just going to be 6, but we'll say 6 sine squared t plus 6 cosine squared t. So it's really just the vector 0, 0, 6. And we need the magnitude of that r prime cross r double prime for our formula, so that's just the magnitude of 6. So our formula, just to recall, curvature is r prime cross r double prime over magnitude r prime cubed. So now we can get the curvature kappa of t. It's going to be 6 over square root 4 plus 5 cosine squared t raised to the 3rd power. So let's check this formula at a couple of points just to see kind of what the curvature looks like. So the curvature at 0 is on the side of the ellipse. So the curvature at 0 would be 6 over the square root of 4 plus 5 cubed, which would be 6 over 27. So the curvature at the side is 6 over 27. What about the curvature at the top, pi over 2? That'd be 6 over square root of 4 cubed, which would be 6 over 8. So there's more curvature at the top of the ellipse than there is at the side of the ellipse. So we can see this ellipse looks something like this. So that's a second curvature formula. Good stuff, good stuff. All right, so just a few more definitions we want to give here. Definition. Recall from, let's see. Okay, so in the derivation, in the skipped derivation, we show that t is orthogonal to t prime. So unit tangent vector is always orthogonal to its derivative, and that's actually in the derivation. So we define a what we call principal normal vector. Principal normal vector. Definition: capital N of t is defined to be t prime of t over its magnitude. So it's a unit normal vector orthogonal to the tangent vector. So principal normal vector N of t. And then if we have t and n, there's actually a vector that is orthogonal to both of those, and we call that the binormal vector. So we define a third orthogonal vector and we call it the binormal vector. So definition, that is going to be the vector b of t equals t cross n. So t of t crossed with n of t. And by properties of the cross product, right, it will be of unit magnitude. So magnitude of the first times magnitude of the second times sine of the angle between them. The angle between them is already pi over 2, so that's just 1. So the binomial vector will also be a unit vector, and it is orthogonal to t and t prime. So that's the binormal vector, capital B of t. Okay, so those are some more terminology that you'll see, at least in the homework. So when you've got these vectors, you can define some planes. So the plane created by, or we could say spanned by, t and n is called the osculating plane. So that's called the osculating plane, and the plane spanned by n and b is called the normal plane. Basically, the normal plane would be perpendicular to the curve the entire way, and then the osculating plane would be tangent to the curve the entire time. So are very very useful concepts in the real world. Normal plane, osculating plane. Osculate means actually it's like Latin for kissing, so it's like just kissing the curve or tangent to the curve. So osculating plane is pretty much what you are when you're on a roller coaster. Like the cart is like the osculating plane, and it's just touching the curve, and the curve is like the roller coaster itself. So you can kind of think of it like that. And the more curvature you have, the more acceleration you feel. So there's a connection there between acceleration and curvature. And if you've had some basic physics, you know, you've seen things like centrifugal force and centripetal acceleration, things like that. So pretty good stuff. So anyway, have a good one. I'll see you guys later.